Hi, we are Xiaoyu and Bingbin. The goal of our project is to close the gap between the human face and manga. First, we do a literature review of previous work. There are two ways to achieve this goal. The first way is to use a style transfer, which is a neural algorithm to turning the artistic style of one picture to other. And the other way is to using GAN. Like the famous pix-to-pix GAN, it can turn the sketch into or the human portrait, which used the paired data to turn the real face into an emoji, and or even cyclogan. Cyclogan can even turn the zebra to a horse and vice versa. So to start with, we use a style transfer.
The style transfer algorithm is based on VGG19 model. We have two input images, one for content and one for style, and the input and the output is a synthesized image with semantic information from the content input and texture from the style input. We use the feature maps as upper layers to represent the content information. And for style information, we use gram matrix to calculate the correlation between feature maps from convolutional layer 1 to 4 and use that correlation to stand for the style. The general procedures is shown in this graph. After initializing our output image using one of the inputs or just white noise, we iteratively update the pixels of output images by minimizing the total loss using back propagation. Next. We convert a picture into 6 different styles.
Yeah, here's our final result. As you can see, there's one major shortcoming of the style transfer, that it basically only extracts the texture of the artistic style and cannot change the ratio between the eyes or the hairs or something, so it cannot change the real picture into a manga style. So we turn to look for the help of GAN. To start with, we need to prepare data set for both real person face and manga face. For real person face, we use a Celeb A dataset, which includes the celebrity images with annotations. And for manga faces, we use Dambro and Getch. And in order to get more rich data, and we build our own dataset, Bingbin, which includes a profile picture for each character with rich metadata. To start with, we try to generate manga faces with DC GAN.
The training data set is Dambro data set. The optimizer we use is Adam. We train this model with 80 approach, and on the left you can see the training loss for both discriminator and generator. And as we can see, along with the training process, the loss for generator is slowly decreasing, and on the right side we displayed several results we obtained from our DC game. As we can see in those 8 pictures, at the very beginning we can hardly see any faces in the results we obtained, and along with the training process, we can after 80 approach we can eventually get some good face results.
In order to achieve the goal of unsupervised cross-domain translation, we first borrow the structure of cyclogan, which includes the encoders and decoders and 2 discriminators to tell that if the generated face is a true picture or a fake picture. And we use a skip connection between the encoder and decoder to retain as much details as possible. And on the bottom is the results of the cyclogan from Jerry Lee. You can see that the cyclogan does generate some meaningful results, But it also loses very crucial informations because the goal of cycle gain is to retain much the consistent cycle consistently loss. But the thing is, it translated so well, and it lost some crucial information such as gender or some other phases doesn't even make sense. So in order to overcome this shortcoming, we add an additional character tags to control the generation results, like to preserving the noticeable visual features such as gender, hair, and eye colors. And in order to get the visual tags, we write a network to extract the tags from illustration in PyTorch. As you can see, the changing of this structure is more like an AC GAN, which the input of the encoder includes not only a picture but also the tags, and the discriminator should also the output of the discriminator should also include the prediction of classification tags. And the whole loss of the network includes the GAN loss, cycle consistency loss, semantic loss, and the classification loss. And here is a network structure of illustration to vector.
The illustration to vector model is based on VGG11. The input is an illustration and the output is a tag vector, which is composed of more than 1,500 feature tags, such as smile, short hair, glasses, and it also gives us the corresponding possibility for each tag. The threshold we set for our outputting tags is 50%. Here, two selling points of this model. First, we replace 3 fully connected layers with 3 convolutional layers and the global average pooling layers. The reason for doing this is because most tags are based on the local information, such as glasses, rather than the global information. And using convolutional layers will be better capturing the local features. Second, we adopt the sigmoid function instead of softmax in the last layers as the activation function, because different from the normal classification problem, which predicts a single value. In this problem, we want to estimate a series of binary values for one input image. And accordingly, we use cross-entropy function as a loss function for the sake of computational cost. We wrote our own I2V model in PyTorch framework and made some major modifications in loading image data, binary hashing, and generating the tag vector. And here is some, and we visualize our results as a video.
Here is a result. As you can see, on the left is the original image, and the output of our illustration to vector network is shown on the right, where we draw the prediction tags with the possibility into the bar graph. Oh, sorry. Okay. In summary, our contribution to this project is: first, we collect and clean the images to build a manga character data set. And second, we wrote and tested style transfer network based on VGG19. And we trained and tested the anime GAN based on DC GAN. And we built a network structure based on BPG GAN and AC GAN to do the cross-domain image translation, which is still unfinished. And we wrote and tuned the IllustraVec network based on VGG11, and we make them demos that can make us smile. In the future, we need to retrain the VGG I2V model with a new Denver rule 2017 dataset, which includes more images with more text. And to finish them, we also need to finish the embedding and training of the PGGAN, XCGAN based on I2V outputs. Okay, here's our references. And thank you to all our collaborators. We cannot achieve this without all of them's assistance. Thank you.